In this particular lecture, I am going to describe algebraic techniques to simplify structures involving products of gamma matrices. This is an extremely useful part of perturbative calculations in field theories, because the setting which we saw in the previous lecture naturally produces this kind of products of gamma matrices, and the efficient way to simplify those products gives rise to quick way of doing those calculations. These objects I will just call as trace theorems. We will see why traces appear. The S matrix framework in the perturbative calculation produces alternating sequence of propagators and vertices. Typically, these are the factors involving p slash for propagators and a slash for the vertices. This whole string of factors coming in this gamma matrix language needs to be simplified to get these answers reduced to numbers. The amplitudes are thus products these factors together with certain projection operators which might come from specific boundary conditions or measurement operators, but we have seen how to express the projection operators also in this gamma matrix language. The probabilities will involve the modulus square of this particular amplitudes, and then when you multiply these matrices and take modulus square, that lead to trace of the values in internal degree. So, this is how we will end up getting traces of these products of gamma matrices, we will see explicit examples of these things in several cases, but this is the generic reason behind it, and so we need techniques to multiply gamma matrices with each other and then evaluate the traces of those products. Now, this can be done in a rather general way based on various identities satisfied by gamma matrices. The simplification of calculation is achieved using the commutation algebra of the gamma matrices and the cyclic nature of trace. By that I mean that the trace of a product of matrices is invariant under cyclic permutation. So, you can evaluate the products in many different ways depending on the convenience. One should note that these properties are independent of choice of representation gamma matrices. In particular, to calculate this various transition probabilities, we do not have to make a specific choice of the Dirac matrices. A specific choice is only useful when you are using certain projections of the amplitudes, and that is used most of the time when you want to write down the wave function itself and how it evolves, but in calculation of the transition probabilities, all those wave functions are contracted with initial and final states, and everything is reduced to numbers, and it is not a particular element of this internal Dirac space. So, the calculation can be done rather straightforwardly without using a specific basis. That is extremely helpful because you can ultimately check the Lorentz covariant nature of these expressions rather easily. If you choose a particular representation, then the Lorentz covariant properties are not so manifest. So, the results are automatically Lorentz covariant. Let us write down the various rules involved. One of them is this Clifford algebra relation, and I want to point out that this relation is dimension independent. On the other hand, there are relations involving the dimensionality of the space explicitly, in particular trace of the identity matrix in this Dirac space is equal to 4, because there are 4 components of the spinor. Also, the Lorentz metric contracted with itself is 4 as well, because there are 4 space time dimensions, but both these quantities are dimension dependent. In general, this object is the number of Dirac components, which is 2 raised to d by 2 in d space time dimension, and this object is nothing but d. It happens that in d equal to 4, these two numbers coincide, but in different number of dimensions they do not have to coincide, and then one can write down more general expressions where these factors or 4 are replaced by dimension dependent quantities. It is useful to keep in mind what kind of identities are dimension independent and what kind of identities are dimension dependent, because one of the well known techniques in doing these calculations in field theory involves analytic continuation in the number of dimensions. Then one has to use suitable expressions which are valid not only for d equal to 4, but also in d different than 4, and then one has to keep track of where the spinor trace is taken and where the Lorentz indices are contracted and work with the algebra appropriately. All these calculations can be easily programmed in a computer, and there are well known software packages which do such algebraic manipulations of the type I am going to illustrate. If you just type in the various products which you want to evaluate, the computer does the calculation and gives you the answer. That also has become very popular because many times the algebra is lengthy and you want to get the result fast and also make sure that you do not make any mistakes in some factors of 2's or 4's, etc., and the computer provides a good check. But one has to keep in mind that sometimes the computers produce their own ambiguous results, and then one has to go back to the theory to figure out what is the part which is not well defined and do the calculation correctly. So, these are all the symbolic manipulation packages. Let me now go to the various useful expressions. The first one I want to mention is a trace of a product of operator, all of them involving A1 slash up to A n slash is equal to 0 for an odd. So, one has to worry about only the products where the number of factors is even. The proof of this result is easily obtained by using the properties of the matrix called gamma 5. This trace can also be written as trace of gamma phi A1 slash to AN slash gamma phi square happens to be 1. The cyclic property of the trace allows you to rewrite this object as this. Then one can anti-commute the gamma phi through the whole string of A slashes, and every time you anti-commute you get a factor of -1. So, to total object gives gamma phi again collected at the end, and since gamma phi square is 1, it can be easily removed. I forgot the trace. The trace is equal to -1 raised to n times the same expression. So, it can be only non-zero when n is even. These are rather straightforward manipulations, but what has gone inside this proof is the fact that we used gamma phi. Once the gamma phi does not exist, which happens in dimensions not equal to 4, this proof will fail, and this kind of identities may not necessarily work. So, we should take a caution that this result is not valid when gamma phi does not exist. Doing calculations with d not equal to 4, you can't just throw out all the odd products of gamma matrices from the traces. You have to evaluate them again by certain manipulations and do the calculations with little more care. The computers can be programmed to do those kind of calculations as well. Let us look at another little example, which is what do the products of even matrices now look like. The simplest case is actually the identity, but the identity trace is 4, as we have already seen. The next one is the product of two gamma matrices. This can be written as A mu B nu trace of gamma mu gamma nu, but this object is symmetric because the trace is a cyclic. So, you can get it in either order, and so the trace gamma mu is nothing but, to be precise, I should put this indices in a proper up and down location. Trace of identity times G mu nu. We have seen the trace of identity is 4, and A mu B nu multiplied by with this Lorentz metric just produces the dot product of the two vectors. This whole object is equal to 4 times A dot B. So, this is a typical example of how various products are manipulated. Now, what we end up doing in larger calculations are nothing but repetitions of this identities involving products of gamma matrices and anti-commutation relations. One can even evaluate the more general structure without taking a trace, where one keeps both the symmetric and the antisymmetric part. So, the symmetric part is what we evaluated over here anyway, and the antisymmetric part of the gamma matrices produces this sigma mu matrix, which we have used many times in earlier discussions of spin and Lorentz transformations. This is again a very simple and useful identity. Now comes the extensions of this identity to larger products. That is the form which is most useful and most frequently included in the calculation. That is generically now just written as what happens to this string A1 slash up to AN slash, how do you evaluate it. The procedure is to use this identity involving two gamma matrices to reduce this trace of n objects to trace of n minus 2 objects, and then use it by induction all the way down till one gets down to product of only two matrices, where the previous identity can be used. So, let us generically work out this induction step. The first point is to just interchange these two objects and see what arises. One can now write trace of A1 slash A2 slash to AN slash, and the Clifford algebra can now give the result of what happens when you permute this A1 and A2. It has a 2 times G mu nu part, which produces 2 A1 dot A2, and then the trace of the remaining part, which now can be A3 slash up to AN slash, and then the term containing gamma matrix in the opposite order, which gives a minus sign contribution with A2 slash A1 slash and then A3 slash all the way to AN slash. So, this procedure is just one use of the Clifford algebra relation, but now we can repeat it in a simple manner, that first we commuted A1 through A2, now A1 is next to A3, we will commute it through A3. So, we will get 2 A1 dot A2 trace A3 slash AN slash as in the first line. The second line will give now 2 times A1 dotted with A3, and then the what remains is the all the factors which are not equal to A1 slash and A3 slash. inside here, and now the sign again flips. So, there is a plus trace of A 2 slash A 3 slash A 1 slash A n slash. So, the signs alternate because that is the anti-commutation rule inside the Clifford algebra. You use it once, you get a negative sign, you use it twice, you get back to the positive sign. So, this now can be repeated every time, getting this 2 A 1 dot A 2 etcetera. The next one will have a minus sign, then the next term, which will be A 1 dot A 4, will have a positive sign, and one can continue all the way till A 1 becomes next to A n, and one should now keep in mind that this product is evaluated only when n was even. So, whenever A 1 becomes next to an even number, the sign is plus, the same as what was there in A 1 dot A 2. So, plus 2 A 1 dot A n trace of A 2 slash all the way till A n minus 1 slash, and then the last object will have a minus sign trace A 2 slash all the way till A n slash, and then A 1 slash at the end. This last object by cyclicity of trace is nothing but trace of A 1 slash A 2 slash all the way up to A n slash, which is what was there on the left hand side to begin with. So, we can shift it to the left hand side, it becomes just twice the contribution, and the 2 can be divided out from the whole calculation. So, we have a final result which is for a product of an even number, we just write all the various dot product of A 1 with all the other matrices one by one. And with alternating signs. And that is the final result, a very useful identity, because n got reduced to n minus 2. There are many such contributions on the right hand side. In particular, there are n minus 1 of them, but each one of them has a shorter product of gamma matrices, and so iteration of the procedure and cutting down the number of products of gamma matrices inside the trace is straightforward, and this is the most frequently used identity in the calculation of S matrix in perturbative field theories. Let me now move to the next identity, which is specific to some other operators which appear inside this calculations. The propagators and vertices always have these slashed operators, but suppose you are measuring some expectation value of a different object or the initial or final states are defined with respect to a certain kind of wave function, one can get an gamma matrix which is not there in the set of these 4 matrices gamma mu, other operators for measurement or specific states can involve the matrix gamma phi explicitly, and that gamma phi is not included in the previous identities which involve only the gamma mu. This is outside the set of gamma mu. So, one knows that the gamma phi anti-commutes with all the other gamma mu, but one can't use the Clifford algebra identity because the G mu nu does not have any meaning when the index becomes 5. So, one has to deal with this gamma phi whenever they appear as a separate objects, and we know certain properties of gamma phi which I can write down. One of them is a trace gamma phi is equal to 0. The other one was that gamma phi is the product of all 4 gamma mu's. Since we can always simplify any expressions involving gamma phi by just writing down these 4 gamma mu explicitly, one can follow the route that in any expression of gamma phi we will first rewrite gamma phi in terms of the gamma mu's, and then we use the previous identities which work very well when there are only gamma mu's are involved. Here the string becomes larger because gamma phi is expanded, but everything else follows straightforwardly. After that, the feature which remains true is that once that rewriting has been done, the only non-zero contribution comes from the parts where each of the gamma mu's is squared to identity. This is a simple consequence of the fact that out of the whole basis of gamma matrices, the only one with a non-zero trace is the identity matrix. Any other product of gamma matrix, they all have 0 trace, and so one can now write down various relevant facts here. Trace of gamma phi with 2 matrices is equal to 0, though in general this rewriting involves 6 gamma matrices, which is an even number, but the whole product is 0 because in the product all the gamma mu's do not appear squared. 2 of them do get square, but the other 2 remain separate. The first non-zero contribution comes where everything gets squared, that is an expression of the form gamma phi multiplied by all the 4 gamma mu's, and this we know what it looks like. We just contract each one of gamma mu with the other one inside this A, B, C, D. Trace of identity after doing square gives 4, and each square basically just produce the identity matrix. This epsilon is a symbol which rewrites gamma phi into these products of 4 gamma matrices with the correct antisymmetric property, and then each one is contracted with this A, B, C, D. So, one can write the result as A alpha, B beta, C gamma, D delta. This is the first non-zero result involving strings of gamma matrices together with gamma phi. Larger expressions can be worked out similarly. Once the gamma phi is rewritten in terms of gamma matrices, one can use the previous induction identities also to go from string of n matrices to string of n minus 2. So, all those results now are possible to calculate. Again, a program can handle these calculations in a rather straightforward fashion. Let me go to the next identity, which is actually not a trace, but it is a part of the calculation which appears frequently due to the dot products arising from Lorentz indices. One can reduce again those dot products to G mu nu and rewrite these expressions by various commutations rules and index contractions. Let us see some examples of it. The first one is rather trivial. It is a product of 2 gamma matrices, which immediately can be rewritten as G mu mu, which we know is equal to 4. The non-trivial part is the next step when you put something in between. So, let us do that. There is one A slash stuck between these 2 gamma mu's, and now we can rewrite this object as explicitly denoting the A component. Then this now can be rewritten with a Clifford algebra identity. there will be A alpha 2 times G mu alpha gamma mu. That is the first part, and the second part is the same object with a opposite order. So, it is A alpha gamma alpha gamma mu, and this is now very easy to rewrite. The G here just contracts the indices between A and gamma. So, we have the usual A slash. Here gamma mu contracted becomes 4, and the first part is again A slash. The final result is minus 2 times A slash. So, the procedure now can be repeated for higher string operators. Let me work out one more example where there are 2 of them in between. I will rewrite this using the same logic. A alpha and then gamma mu gamma alpha, I will just rewrite as 2 G mu alpha minus the opposite order the result is A alpha multiplied by 2 G mu alpha minus gamma alpha gamma mu, which is the Clifford algebra used on this product gamma mu A slash, and then the B slash gamma mu remains as it is. So, now one can reduce this object in a rather straightforward fashion. This alpha will become the same index as mu because of this metric, and then it is multiplied on the other side. So, it becomes 2 B slash A slash, and this object we have already seen how to simplify in the previous results. So, it is minus A slash and gamma mu B slash gamma mu is equal to minus 2 B slash. This can be rewritten as 2 times B slash A slash plus A slash B slash, and so one has the same product, but with opposite order of gamma mu inside here, which is exactly the form that can be simplified using Clifford algebra once again. Then the result is the G mu sandwich between these 2 operators B and A, and that result is 4 times A dot B. So, this is the kind of illustration that one can use these identities repeatedly to simplify this contracted gamma matrices. I will not work out many more cases, but just write down some of the results which can be proved in a rather straightforward fashion. What happens when there are 3 of them sandwiched in between? The result is minus 2, but then this product appears in opposite sequence. When there are 4, one get similar result with the gamma mu disappearing, and one can actually again use the iterative procedure to reduce it to 3 slashes sandwiched between gamma matrices and using the earlier results. This gives the result that looks like this, and the previous one are basically contractions of all the Lorentz indices of gamma matrices and how they simplify the algebra. We have not included any traces inside here, but the fact that there are 4 values for the Lorentz indices has been explicitly used in this calculation. Let me mention one more general result which illustrates a different symmetry in doing this particular calculation, and that result is the trace of n gamma matrices is equal to the trace evaluated with exactly opposite order, and we have seen that this one is non-zero only when the number of factors involved is even. This property follows from charge conjugation invariance of the electromagnetic interactions that we have seen before. In particular, the matrix C exists such that C gamma mu C inverse is equal to minus gamma mu transpose. One can just insert C and C inverse between each A I slash and A I plus 1 slash and rewrite this whole string, and C multiplied by C inverse of course is a trivial insertion of identity. So, the value does not change, but then the expression can be now rewritten using all this transposes involved. So, one can see that the expression becomes with the trivial insertion of C inverse and C together with the cyclic property of the trace. Now, we can substitute for every part this identity involving gamma mu transforming to its transpose. There are so many factors which gives minus 1 raised to n, and then the trace is now A 1 slash transpose, A 2 slash transpose, etc. A n slash transpose, but the transpose of individual factors is equal to the transpose of the whole product written in an opposite sequence. So, this is now equal to trace of A n slash A 1 slash the transpose first, and then the trace, where trace of a matrix and its transpose are equal, and the number n is even. So, that together gives the result that we wanted. This is a important result which connects the particle description of evaluating the matrix elements and the antiparticle description, because when one evaluates the Feynman diagrams, the products are described according to the direction of the arrow. This sequence with opposite order corresponds to flipping the direction of the arrow and then evaluating the trace. Flipping of the direction of the arrow is equivalent to going from particle description to antiparticle description. That is a useful property to have and also to understand. These are some of the basic ingredients for evaluating products of gamma matrices in terms of numbers, and the calculations make full use of these tricks which I have illustrated. Now, we can move on to the next step in the description of the theory, and that is an extension of what we have done so far, is to calculate general fermions evolving in a background electromagnetic field which is described by the term A slash. In our description so far, we have used the potential model description, which is common in non-relativistic mechanics, where the electromagnetic field is provided as a background and in which these charged particles are going to propagate, and all which we have done so far is a machinery which allows this kind of calculation. To go further, we need a more general framework. Where the electromagnetic field also evolves due to its interaction with charged particles. Once we do that, we will have both the electrons and the photons becoming dynamical degrees of freedom, and then we have a complete theory of quantum electrodynamics. The ingredients for making photons dynamical we already have, those are the Maxwell's equations, and we will now see how to include Maxwell's equations and its own framework in this propagator theory in the next lecture.